Welcome, my friends! In this video, we will discuss how to complete a one-sample hypothesis test for the population proportion using p-values. Remember that the population proportion p is just the probability of success from the binomial distribution, such as the proportion of voters who support a political candidate or the proportion of students in a statistics class who receive an A. The procedure for testing a proportion in a nutshell is formulate a hypothesis about the population proportion of some variable that you would like to research. This will typically be a claim, such as that the proportion is either greater than, less than, or not equal to some specified value. Gather a sample from the population to see if the data is consistent with your hypothesis. This includes calculations involving probability and the standard normal z-distribution. If the data is highly consistent with your hypothesis, you will conclude that your hypothesis is most likely correct. Otherwise, you will dismiss the hypothesis. There are a few assumptions that must be met in order to complete a hypothesis test for the population proportion. First, a random sample must be used to gather the data. Also, n times p sub 0 and n times 1 minus p sub 0 must both be at least 5. N is just the sample size, and p sub 0 is the hypothesized value for the population proportion. This is so that the central limit theorem will apply, meaning we can use the z-distribution. Some instructors or books require that n times p sub 0 and n times 1 minus p sub 0 must be at least 10 or perhaps 15. In completing the hypothesis test, we will need to take a sample and calculate the test statistic, which in this case will be a z-score. The formula for the z-score is z equals p hat minus p sub 0 divided by the square root of p sub 0 times 1 minus p sub 0 divided by n, where p hat is x divided by n and is the proportion of successes from the sample, x is the number of successes from the sample, n is the sample size, and p sub 0 is the hypothesized value of the population proportion. Essentially, we are comparing the sample proportion p hat to the stated population proportion p sub 0. The test statistic will tell us how many standard deviations away from the mean our sampled p hat is, assuming that the null hypothesis is true. Let's take a look at an example. A certain city has an upcoming mayoral race, and a political polling organization is interested in the proportion of likely voters who support the front-running candidate. If less than 50% of likely voters support the candidate, a new advertising campaign will be started. From a random sample of 300 likely voters, 135 support the candidate. Is there sufficient evidence to suggest that the proportion of likely voters who support the front-running candidate is less than 50%? Use a 0.01 level of significance. Let's begin by writing out some of the given information. The default position is that the proportion of likely voters who support the candidate is 50%. Therefore, p sub 0 is 0.5. The sub 0 just means that this is the proportion corresponding to the null hypothesis, which we will be testing our data against. X, the number of successes, is the 135 supporters, and n is the sample size of 300. P hat is x divided by n, or 135 divided by 300, which equals 0.45. Note that the assumptions for this test are met, as we have a random sample, and both n times p sub 0 and n times 1 minus p sub 0 are much greater than 5. Let's move on to the 3 steps of the hypothesis testing procedure. Step 1. The null and alternative hypotheses. Every hypothesis test will have a null and alternative hypothesis, denoted by h sub 0 and h sub a. Since we are testing the population proportion, both the null and alternative hypotheses will start with p. The alternative hypothesis typically corresponds to the research question that needs to be tested. In this case, if the proportion of likely voters who support the front-running candidate is less than 50%. Therefore, the alternative hypothesis is p is less than 0.5. The null hypothesis always contains an equal to sign, so we have p is equal to 0.5. Step 2. Calculations. This is where we must calculate the test statistic with the formula that we discussed earlier. Plugging into the formula, we have this result. Take a moment to make sure you can verify where all of the values in the formula are coming from. In the TI-84 calculator, or any scientific calculator, type open parentheses 0.45 minus 0.5, close parentheses, divided by the square root of 0.5 times, open parentheses, 1 minus 0.5, close parentheses, and then divide by 300. And potentially close parentheses one more time if your calculator doesn't have the square root image like mine does. We get negative 1.73, rounded to 2 decimal places, for the test statistic. If we draw the standard normal z distribution, we know the z-score of 0 corresponds to the mean, and we just calculated that the test statistic is negative 1.73. We need to calculate the p-value now, which is the area in the tail, which I have shaded in green. We could calculate the p-value using probability tables or computer software, but today I will be using the TI-84 calculator. To calculate the p-value, press second, distribution under the vars key, option 2 for normal CDF, and then we are asked for the lower and upper bound. We will be entering in z-scores to the calculator, and we need the lower and upper bounds of the shaded area on our graph. The lower bound of the green shaded area is negative infinity. The distribution technically goes on forever in the negative direction, but we can put in negative 1,000 to represent 1,000 standard deviations below the mean, which will represent negative infinity. The upper bound is our test statistic of negative 1.73. Leave the mean at 0 and the standard deviation at 1 for the standard normal z distribution. Scroll down and paste. On a TI-83 calculator, match this output. Normal CDF, negative 1,000, negative 1.73, 0, 1. Press enter, and we have the p-value, which is 0.0418. I generally like to round p-values to 4 decimal places. This is the area in the left tail of the distribution, and is the probability of sampling a sample proportion of 0.45 or less from a sample size of 300, assuming that the null hypothesis is true. Step 3. Decision and conclusion. If the p-value is less than or equal to alpha, we reject the null hypothesis, and if the p-value is greater than alpha, we fail to reject the null hypothesis. As I like to say, if the p-value is low, the null has to go, and if the p-value is high, the null will fly. Anyways, the level of significance alpha is equal to 0.01. The 0.0418 p-value is greater than 0.01. The p-value is greater than the level of significance, so therefore we fail to reject the null hypothesis. Notice that the p-value is less than 0.05, which is another common value for the level of significance. If we were to test this hypothesis at the 0.05 level, we would reject the null hypothesis. For our conclusion, we say that at the 1% level of significance, there is not enough evidence to suggest that the population proportion of likely voters who support the front-running mayoral candidate is less than 50%. And we are done. Alright, my friends, that wraps up our discussion of the one sample proportion hypothesis test using p-values. We will be exploring many more fun and exciting statistical topics that you won't want to miss, so make sure to check out our other videos.